Good afternoon. My name is John Stone, and I'm the main developer of Visual Molecular Dynamics. I work at University of Illinois, and we're a NIH-funded research laboratory that develops tools for molecular modeling and various types of biological simulation. So the goal of our software tools are to enable scientists to simulate large biological systems, to understand their structure and function. And of course, in times like today, with things like COVID being studied in great detail, these are very large structures and very challenging systems. And we need to be able to run simulations of virus structures and the various components of the virus on large HPC systems. So our software has been used for multiple decades to do these kinds of simulations, and the ongoing improvements in cryo-electron microscopy imaging techniques have allowed us to study ever larger systems over time. The sort of state of the art today are these large viruses as an HIV capsid. The COVID virus is another several times larger, large photosynthetic organelles, and even we're getting into the regime now where it is just beginning to become possible to simulate prototypical cells, so the minimum sized life forms that can exist on their own, you might say. So supporting this work, I'm going to tell you a little bit about how we ported our software to ARM and how we evaluated its performance. We did this work in conjunction with Oak Ridge National Laboratory using their Wombat cluster. We used two different types of nodes, the Marvel Thunder X2 ARM processors, which were combined with NVIDIA Voltas. And also most recently, Oak Ridge has installed some Fujitsu A64FX nodes. And with those, we've been able to do some work with SVE vectorization for the first time. So the first application is NAMD. This is our parallel molecular dynamics software. It's used in biophysics and structural biology, and it's written in Charm++ and CUDA. And so Charm++ is a parallel programming runtime system developed at University of Illinois by Sanjay Kalei, and that's how we do things like message passing on large-scale machines. Our porting experience was very good. We had NAMD running on various machines over the years, and it's a very portable piece of code. I think it took us about an hour and a half to compile NAMD and all of its dependencies from scratch. That was a great experience. It was very easy for us to get up and running on the ARM platform. I think we just had a few tweaks to the code in our build system to enable it to compile with the CUDA 10.2, which was new at the time we did the port. So our software is now ARM ready, and it gives correct results, and we've compared that. Sort of the ongoing work that we have to do for NAMD is to begin doing multi-node benchmarks on clusters. And so that's ongoing work, and we hope to have new results there soon. For our initial analysis of performance on ARM, we compared NAMD's single node performance between three different platforms. So the top line is NVIDIA DGX2. This is a big multi-GPU machine we have at Illinois. It's based on the SXM2 form factor. These are the high power dense GPUs that are found in supercomputers. And we report the results in terms of nanoseconds per day. That's the amount of simulation time that a scientist gets if they run the software for a particular molecular structure for a whole day. So we ran this on a 99,000 atom structure called apolipoprotein. And so that's our benchmark metric to compare against. This is the most highly optimized version of the software. We ran the same test on an IBM AC'22. That's a Power9 machine, basically one of the Summit nodes, and running with the same type of GPU, but it's worth noting that on this platform, the host and the GPUs are attached through NVLink rather than PCI Express. And so that platform did roughly the same result. It doesn't benefit as much from CPU side vectorization, so that's worth noting. And then we have the new ARM result. Now it's noteworthy here that because we had to use a PCI-based host machine rather than one of the HPC specific form factors, this used a regular run-of-the-mill PCI card. They run at a very slightly lower clock rate, so there's about a 10-15% difference in performance of the hardware. So it's not quite apples to apples, but you can see we get very nearly the same performance on the ARM test box that we do on the other two. So this is a very satisfying result. This is great, great outcome. This is, again, a single node run on just a single GPU, but basically what I would conclude with here is that there were no surprises. It was straightforward work, and we expect that ongoing work to optimize NAMD for ARM will close remaining gaps. And I hope we can do more of an apples to comparison when we have other hardware available to us for testing. So I work on VMD primarily, which is our visualization and analysis software. It's used to prepare, visualize, and analyze all the molecular simulations. And it's sort of the go-between for scientists between experimental structure information and the simulations that we run on the supercomputers. So it's responsible for helping them build and analyze all these simulations. So VMD, because it's visualization heavy, it uses a lot of libraries to do things like hardware accelerated ray tracing. So there we did some work with early pre-release versions of libraries. So it took me, I think, more like a day to do my port, but I had these dependencies to work out, and I had to ask NVIDIA for some help to get access to early versions of these things. I just did single node tests. But I'll show you some of our early results. My summary would be, again, we're quite happy. The ARM performance is comparable to what we get on x86 and Power9. And the real area where I need to do additional work is just in making better exploitation of ARM vectorization to speed up some of the things that we don't put on the GPUs. There's sort of the molecular preprocessing that gets done before data is sent to the GPUs for the dense number crunching. So here we have a comparison of the three platforms for density map segmentation. This is basically taking a cryo-electron microscope density map and doing some analysis so that we can identify connected subregions of the density. This allows the scientists to more easily label and operate on different parts of the atomic structure, and to do things like align atomic structures to these microscopy density maps. So we put this on single GPU. Again, here we're comparing V100 GPUs again. The Power9 is an SXM module, so that's a little higher clock rate, but the CPU, the Intel and the ARM versions are both PCI Express. Here we see the differences in performance. I would call these, although there's a spread of about 20% here, I'd say they're roughly the same. There are some differences, and Power9 has a little bit longer CUDA kernel launch latency, and neither Power9 nor the Thunder X2 are getting the benefit from the hand-coded vectorization that's been done on the host that x86 enjoys. And so I'm expecting that after I do the same work on ARM, we'll be able to close the gap there. So that's very exciting. So here's a cross-correlation calculation. This is taking these cryo-electron density maps and measuring their quality of fit with an atomic structure. This is a complicated, statistical analysis that's volumetric in nature, and it has a lot of memory references as well as flops. And there's a lot of data transfers between the host and the device. So here again, we have the three test platforms, and we see roughly comparable results. Again, Power9 benefits from having an NVLink connectivity to the host a little bit, but it loses a little performance due to kernel launch latencies. In the case of the ARM platform, we don't have the high clock rate GPU here, and we don't have the CPU vectorized pre-processing yet. But this is a pretty good result, and I'm satisfied with that. And here we have calculation of molecular orbitals. So this is used for visualization and analysis of quantum chemistry calculations. We've got a multi-GPU algorithm here, and basically it's calculating a three-dimensional molecular orbital amplitude or electron density in a 3D grid from various Gaussian orbital basis sets. And we can compute this in a bunch of slices. So the decomposition is sort of a round robin dynamic decomposition over GPUs with different GPUs computing slices of this 3D grid and then sending them back to the host. And because there's a non-trivial amount of data transfer, you'll see that NVLink gives a performance boost that's noteworthy on Power9. But here again, if we look at how ARM turns out against x86, they're very comparable. They're roughly similar runtime. Again, x86 is getting a little benefit from CPU vectorization of some of the setup routines, but the overall performance is roughly the same, especially with two GPUs. We're only, a hundredth of a second apart on the runtime. So that's very good. Some of the most recent work that I've done, Oak Ridge just installed new Fujitsu FXA A64FX compute nodes that have SVE vectorization and hardware. And so this has created an opportunity to make VMD capable of doing runtime CPU dispatch. And this allows us to launch processor-specific kernels that exploit different enhanced instruction sets. So for example, in the case of ARM, we've got both Neon or SVE, which can be optionally available. So on the two types of nodes that Oak Ridge has in the Wombat cluster, this means VMD can detect which types of instruction sets are available, and the same shrink-wrapped binary can run on either processor with peak performance. So this is great. And of course, we have runtime detection of GPUs. So really, this means that with a single ARM64 binary, a user would be able to run on any of these different combinations of hardware, and they would get the best performance that's available on the machine they're using. So some of the first things that need to be vectorized to bring ARM performance up to where the x86 kernels are, even with CUDA, is to bring vectorization to some of the analytical kernels that are used heavily in the setup of these GPU accelerated calculations. So most of these are memory bandwidth bound kernels, but they do benefit from vectorization. So just as an example, I did a few of the simple analytical kernels, and we get roughly a factor of 3.8 performance increase going from straight C++ to handwritten SVE. One of the things, this was really my first exposure to SVE. And so going into it, I had sort of expected an experience that was similar to what I went through when I ported these kernels to AVX2 or AVX512 or other vector instruction sets that I've written kernels for. But I found that, in fact, I was very surprised. SVE was a lot easier for me to use. The variable length vector approach that it uses is made very simple through the use. It's pervasive use of predication on all the operations. So this means you have a little predicate flag set that goes along with every one of the operations that you're doing. And by using those, you no longer have to deal with handwriting loops that process heads and tails of non-vector sized or non-vector aligned operands, things like this. And this makes it a lot easier to write those kernels. And I'll show you an example in a couple of slides. I'm still doing a lot of development and benchmarking here. And in particular, I'm going to get into some of the meatier kernels, but I'm expecting them to be a lot cleaner and simpler to write than some of the ones I did on other architectures. One of the things that I thought was interesting, I did a little literature search about variable length vectorization. And one of the conclusions in an interesting paper I saw was that you're going to pay something for carrying around these predication vectors that allow the hardware to keep track of which SIMD lanes are active or inhibited. But that cost is very low. And so you might give up something versus a fixed size, perfectly structured vector approach, but at most this is, in their measurements, maybe 10% cost. And I think, depending on the code you're dealing with, for a meaty loop, the cost can be a lot lower than that. So I'm curious to see how that works out in practice when I get to much larger kernels, but I'll show you kind of what that looks like in the next slide here. So on the left, I've taken a very simple piece of code that's used in VMD to pre-process some density maps when they're first loaded into the program. This is, it's not particularly relevant to any of the benchmarks I showed, but this is a very simple loop, so I chose it as an example. So on the left, we have the x86 AVX implementation, and I've chopped out various complicated things here just so it's sort of minimalistic. And one of the things you'll notice is that this implementation has to have a section where we have a loop that rolls up to an address aligned boundary. And this is important so that we're going to ensure that we have the vector achieving memory alignment. That's something we have to do on x86. Whoops. And that adds some complexity. Whoops. And we have then we have a loop that processes all the elements. And so this is where the meat of the work occurs. Then we have a remainder loop, which is similar to this, that processes any straggling tail. And then after that, we have to do a sum reduction of the vector sums in the final results. Or in the case of min or max, we have to do a vector min and max. And on the right, we have the SVE version. And we're basically doing the same thing, but here we have predicate variable. So this is PG. And it begins with all the predicates set to true. We initialize min and max, just like we do over here. But then once the loop begins, we don't have to worry about dealing with the head or the tail issues, because that's addressed by the predicate test. So we have an SV while less than, and this basically compares the current SIMD lane to see if it's less than or equal to the number that we're processing, and it will set the predication bits appropriately for the SIMD lanes that are active. And then we use that in all of our subsequent vector instructions. So we load those elements from memory, then we compute the new minimum value among the newly loaded vector, the new maximum value, and so on. And then we continue this loop. And because we get this predication handling all the rough edges, there's no cleanup loop and there's no pre-roll up loop before or after. And you can see the entire kernel is now on this simple page of text. So very easy to understand. And with that, I'll say thank you and acknowledge my colleagues at University of Illinois, and thank Oak Ridge National Laboratory for their assistance in letting us port our code.